Hi, my name is Bruce Kranhoff, and this is a NeurIPS review presentation on some stuff that I learned at NeurIPS. And this particular presentation is focusing on a bunch of miscellaneous stuff I saw that I thought was interesting or useful, but doesn't kind of fit into the other two presentations. So the first thing to talk about is neural tangent kernels. So basically, as neural networks layers approach the infinite width regime, their ultimate predictions after training becomes predictable. This is providing of a random init. And we can start to prove certain theoretical things, like training error goes to 0. Not surprising when you have an infinite number of widths. Yeah, so this is, I'd say, theoretically interesting. However, what it converges to, like we know it always converges to the same thing, what it converges to is a kernel. So to make a new prediction, we need to take into account all the other data points and I think do some large matrix multiplications. So it's not practically feasible, right? Because neural networks, ultimately why they work so well is we've got lots of weights and we also have large data sets, right? And then we do things like data augmentation that basically makes the amount of data even more, same as dropout. And so if you need to kind of have you need to use every single data point whenever you want to make one additional prediction. It's not very feasible. So they're interesting, they're all over the place. Maybe the theory that's developed using them will lead to some useful outcomes, but in terms of being practically useful, my takeaway is they are not. And the title here pretty much sums it up. Wide neural networks of any architecture are Gaussian processes. So yeah, Gaussian processes is a type of kernel process where knowing all the data points, you can make a prediction at a new location and an uncertainty at that new location. Okay, so I saw something about adversarial training significantly improving classification. I believe this was on ImageNet. So I think adversarial training is basically you're augmenting the data, right? So you're going to change an image slightly, and then you still want to predict the same label. So it's just another way rather than the slightly skewing or rotating or shifting your image. This is another, or changing the colors a bit. Adversarial augmentations adversarial examples are another way to augment your image. And interestingly, it leads to neural networks with lower Lipschitz bounds, which is another paper covers how to calculate or estimate these Lipschitz constants. Yeah, so the big takeaway though is like we can get significantly better performance on image classification, probably other image tasks. Maybe this applies to audio as well, because there's like continuous time in audio. I think it has to do with there being some kind of continuous type variable that you can do these adversarial augmentations. And you can get significantly better results. All right, variational inference. Something I learned about recently. I understand the basic theory and some applications. Unfortunately, I'm not super familiar with this, so I wasn't able to easily, at least, follow what most of the papers were doing. But at least in theory, variational inference seems to be widely applied now, and I know going way back, it's being useful in practice as well. So yeah, my big takeaway is variational inference is important, and there's probably going to be some important new applications of it that have come out or are coming out soon. All right, so I mentioned this previously. So calculating the Lipschitz constant exactly for a neural network is NP hard, but this paper comes up with an efficient way to estimate or bound the Lipschitz constant for deep neural networks. And yeah, a low Lipschitz constant is expected to generalize better, so provide more robustness, because if nearby points should then map to similar predictions if there's a low Lipschitz constant. Yeah, and so yeah, this is interesting that they have this. Maybe having this bound, maybe we can now regularize using that bound to get better results, right? It will be interesting to see how they use this. All right, I found this quite interesting. So there's this intuition covered in our reading group and talked about elsewhere that, you know, it's good to have a larger learning rate, smaller batch size initially, and then you can increase the batch size or lower the learning rate later on. So I guess this kind of shows one of the effects that explains why this is. So the graph shows the results, the outcome. No matter what, you get to 0 training error. But for your validation accuracy, you can see that if you initially had a higher learning rate, then later on at the end you'll have a lower error. You'll have a lower validation error. I don't know what this is about. And there's an example that explains this better, but with a small learning rate, you can memorize these hard-to-fit class signatures, whereas a large learning rate with all the noise doesn't let you learn these hard-to-fit class signatures. So you only learn to use the easy-to-fit patterns first. And you'll only learn these later on when you anneal the learning rate. So this example shows it beautifully. So create a data set with 20% regular images, 20% just these patterns here. So they've made up these patterns where each of these patterns corresponds to a certain class, right? So this is like an encoding of the label. But this encoding, it's got some very complicated structure, so you'll need a lot of nonlinearities that are finely tuned in order to be able to use this for prediction. And then 60% is both of them. And so when you have a small learning rate, it will be able to finely tune how to use this pattern, right? And so it will learn to classify this 80%, and then it'll only, to learn how to use the actual images, it'll only use this 20% of remaining examples, right? And so you can imagine like some pattern like this. I mean, this could just be by random chance, there was a certain pattern in certain complicated pattern in all of the examples of a certain class, right? Or most of the examples. And so a small learning rate will allow you to overfit to that coincidental complicated pattern. Whereas a large learning rate can't finely tune the weights to fit those patterns at first. The large learning rate, therefore, learns to, it uses this 80%, and it finds easier to fit features and fits those first. And then only once the learning rate is lowered does it learn these hard to fit patterns, and only on this 20% of examples, right? Yeah, so basically the large initial learning rate, all that noise is reducing the capacity, of the neural network to overfit to these complicated patterns. And so the neural network learns to use the easy to fit patterns first, like it has less representational power. And then as you lower the learning rate, you're basically increasing the representational power so that you can ultimately fit everything. And I wonder, I mean, so a larger learning rate causes more noise, right? And I can see that different learning algorithms are going to give you somewhat different noise as well, which I'm not clear what effect that has. And all right, so an insight I had related to this is, well, basically we're using the noise here to reduce the capacity of our neural network so that we don't overfit to these complicated patterns. Well, another way that we add noise is like dropout, right? Or stochastic regularization. So maybe it's a good idea to initially have high dropout and then gradually lower the dropout, right? I think it makes a lot of sense to me. Cool. I think I went in the wrong direction. Yeah, there we go. All right. NLP has been progressing rapidly. That's my main takeaway. They made this benchmark glue that highlighted where NLP algorithms were still subhuman in their performance, and within half a year, they were beating an average human. So then they made super glue, an even harder benchmark of the things that still had not been beaten. And then within half a year, the machines were at 98, where 100 is what how an average human would perform. So almost at human performance, probably beaten human performance. It's probably beaten human performance by now. So yeah, so rapid progress. All right, so this is quite an interesting application of machine learning. So what they found is they put some mice through a prolonged stressful experience, basically being beat up and then being put in the cell right next to the mouse that beat them up. So they're not beaten up anymore, but they're still, stress response is still on. And they did that for 10 days. Every day got beat up and then spent the rest of the day with only a screen between it and the mouse that beat it up. And this stressful ordeal would put 60% of the mice into depression, but then 40% wouldn't get depressed. So what's the difference? Can we figure out something ahead of time that predicts which mouse will get depressed and which will not? Well, they had electrodes or stuff in the mice, and they were able to extract brainwave signatures of vulnerability to depression. That if a mouse was vulnerable, it was very likely to get depressed. If it was not vulnerable, it was very unlikely to get depressed after the ordeal. And so then they looked at, what can put the mice into this vulnerable state? Well, childhood trauma, we know that for humans, they traumatize some mice. There's this molecule, sidekick 1, interferon alpha. When you're sick, you have this, it makes you feel crappy. And being female. Females are more likely to be depressed, and they're more likely to end up in this vulnerable state. And interestingly, now that they can measure whether somebody's in this vulnerable state, they were able to measure that antidepressants would move at least mice back from the disease state to, which is depression, to the vulnerable state, but not back to the resilient state. So we can now measure what we know, which is that somebody who's being depressed is much more likely to become depressed again later on in their life. And because we can now measure that they're going to be in this vulnerable state, that we don't know how to actually make people resilient. But hopefully now that we can measure this, hopefully now it'll be easier to find drugs and other interventions that might help people actually get back to the resilient state. So quite an exciting application of machine learning, I think, in terms of making a difference for the world here. All right, so this is one of the novel New Direction papers, like honorable mention or whatnot. Now, one of the things that I thought is why machine learning works so well now is that we're doing end-to-end training. In images before, we used to handcraft certain features and then put it through an SVM or that kind of thing. With machine translation, I think we would parse things, then we do this step, and then we put it through this, and then we do a beam search thing. There's like all these steps that are kind of human engineered. And it kind of works, right? And it worked with our computational power of the day. But now what we do is we say, okay, here's your input, here's your output. We have massive computational power. Just figure out all the weights in between to get the best output you can given the input. And this works fantastic with lots of computational power and lots of data, right? But interestingly, this is showing that end-to-end training is maybe not what's essential. What's essential is, I guess, not having handcrafted or hand-engineered features and processes, but rather having something that's automatically learned. So in this case, what this paper does is that they maximize mutual information. So if it's a time series type thing, it would be between temporally nearby representations, or for images, it would be patches of the image. So you've got a patch here, and you extract some features. And these features come from the same image, so they should somehow be related, right? And so you can maximize, I guess, the mutual information at this next level of features here. And then you can build layer upon layer that way, just maximizing mutual information. Yeah, and so this is a kind of unsupervised learning, right? We're not using labels. We're just, maximizing mutual information as a way to extract features. And then we take the final layer's results and put it through a single layer that is trained on our objective. And sometimes they found they needed one additional layer in order to make good predictions. And it performed quite well on some data sets I'm not familiar with. I'm not sure why they were using such, I wonder if this is overfit to that particular data set. And so an advantage of this, I don't think, this doesn't seem to be ready for prime time yet, but possibly in the future, if this becomes a thing, an advantage is that you don't need end-to-end optimization. And this means you can just train a small part at a time, right? You could train a small part of a huge neural network that could easily fit on a single GPU, or maybe it could also just fit locally on your cell phone or something. So this will distribute well. This will work well for parallel training. So this just seemed like an interesting idea. So attention involves doing dot products to figure out how much weight to put on each thing. And so doing attention over a large number of keys becomes quite expensive. So if you want 10 to the 6 keys, the cost becomes prohibitive. But we might want to have kind of large memories or large spaces to pay attention over, right? So the solution in this paper is product key factorization. So you can take the 10 to the 6 keys and say, okay, I'm going to make 10 to the 3 half keys and another 10 to the 3 half keys. And then by combining those in all possible ways, I can get 10 to the 6 keys. But now I only need to do 10 to the 3 half key dot products plus another 10 to the 3 half key dot products. And then you can add those together in a certain way. And you can see that will allow you to easily see which ones have the highest kind of matching, the largest dot product. That's the nearest neighbors thing. And then I think to keep things feasible, if you're going to do attention, you need to only do attention over a subset. Like maybe you take the 10 to the 3 top matches, and you just do attention over those. So here, this is depicted quite clearly. I think you've got your first half key and keys and your second half keys, and you can combine these 3 of each of these to get 9 product keys, right? So a neat idea. A neat idea for when you want to do attention over very large sets. All right. So I went to the meta-learning workshop. I think that was on Friday at NeurIPS. And my main takeaway is that meta-learning, it's a cool idea, a very attractive idea, but it's still very experimental and not working very well. And we'll talk about that. So WarpGrad was, I thought, the most interesting thing I learned there. And so if you're familiar with MAML, it learns an optimization for the weights such that a single step of SGD will make the most progress possible on that subproblem. So in meta learning, you've got a whole bunch, you have a whole class of problems, right? And you want to be able to quickly adapt to each problem. Well, WarpGrad instead says, let's optimize so that no matter where the weights are, and no matter what the problem you've selected from your class of all the problems, your gradient is kind of pointing in the best direction. So it kind of warps the gradients so that SGD works as quickly as possible. And we can see here, this is the objective. So we're taking a gradient with respect to the thetas, which are our task parameters. And then we take a step. And so this would give us our next value of theta. And then at our next value of theta, we're going to evaluate that. And this is now our meta objective. And this is what we want to see. So we'd want to minimize this. So after one step, we want to minimize this where we're averaging over all possible initial thetas drawn from some probability distribution and all possible tasks. And we want to minimize this loss function over these other parameters, phi. So our neural network now has a mix of like parameters theta and phi. And so the theta parameters are kind of task specific, they get minimized. The phi parameters are the ones that don't get changed. They should work for any task and any theta. The phi parameters should kind of warp the space so that at each step we make as much progress as possible. Yeah, I thought this was pretty interesting. And what they did in the paper is like, this was helpful, but then they also optimized the theta using MAML, and then they optimized the phi using this method. Yeah, so MAML only is optimized for a single step, whereas this is optimized now for a whole bunch of steps. And yeah, apparently this is supposed to help with continual learning. I don't quite get this, but so the problem of catastrophic forgetting when you train on a new problem while you destroy the tweaking of the weights for your old problem, well, it can help to avoid that. So then IID data becomes less important once you get around catastrophic forgetting. So an interesting algorithm that looks like it has potential, but overall, meta learning doesn't seem to work very well. So they're overfitting the benchmarks. So this poster investigates how well is meta learning working. They're overfitting the benchmarks, and nothing really beats fine-tuning pre-trained weights and transductive learning. So fine-tuning pre-trained weights is where you take a neural network trained on ImageNet, and then you use it for your new image task, and you just change the weights a little bit, but you start off the weights at that initialization. And transductive learning, that's where you make new predictions using previous predictions. Yeah, the definition is here. I'm guessing what they do is in meta learning, there's a bunch of different tasks, right? And you don't know what task you need to do. But you get a few examples from a task, and then using those examples, you try to make the best prediction possible. Well, I'm guessing what they do is they just give as input, okay, here are some examples of inputs and outputs. And then here's a new input, and you want to make a prediction for the new input. So kind of they just give all of that as input, I'm guessing. So that would be a fairly simple approach. I'm not sure if I'm explaining it well. But yeah, they don't use MAML, or the best results are not obtained using MAML. All right, and that is it. Thank you for watching this presentation, these presentations. Bye-bye.